The tectonic forces and the related thermal effects we are going to see. Tectonic forces can open up basins so that the sea level can fall, and since the new crust is produced by stretching, the new oceanic crust can be hot and it can increase the volume of the water that is in contact with it. Say the continents got separated in this way, so the new basin is produced. Here the water level may fall. So also here an opening has happened and the water level can fall. Now for a slow mid-ocean ridge spreading, there is a good amount of time for the water to get adjusted with the temperature and not much volume change will happen. But if the fast mid-oceanic ridge spreading happens and the oceanic crust is produced abruptly and is hot, it will increase the temperature of the water, water will increase its volume and can spill on both sides. These have been reported. The role of ice cap formation I have already described in previous NPTEL lectures, that when the ice melts, it can increase the volume of the seawater, so the water level can rise, and conversely in case of a global cooling, water that evaporates here and goes to the continent and falls as a rainwater will be more and more preserved in the continent, so that the water level in the sea can fall. Changes in the rate of seafloor spreading result in eustatic sea level changes. Tectonics induced sea level rise will be essentially slow because the plates amalgamation or breakup is a very slow process. When we talk about the glacio-eustasy, there are cases of documented raised beaches, and these testify the periods of higher sea level in interglacial periods. Interglacial period means between two glacial periods. Between two glacial periods there was heating and the ice melted, therefore higher areas appeared as beaches. These raised beaches have been documented. They were true beaches when the glacial period was persisting. How much water in the global water budget stays in the continent as rivers, lakes and groundwater also is important. Suppose that content has increased, in that case the sea level can fall, or if this content is reduced, sea level is going to rise. A cyclicity in the changes in the sea level has been reported by several publications. It looks like there is a hierarchy of cycles of sea level fluctuation through the Phanerozoic. There can be shorter term variation of sea level and there are also longer term variation in sea level. So different cyclic stages have been identified, the first order cycles. For the Phanerozoic, the long term fluctuation in sea level are presented by these curves, and these are related with large scale plate movements. The first order cycle is a smoothed out curve. Out of this we can make a smooth curve, and that shows the first order cycle or the overall pattern. We note first there is a rise in sea level, and then from here to there a fall, and then nearly the same, and then there is an overall rise followed by an overall fall. When we were tracking from more than 500 million year here up to the present 0 million year, and we have crossed Phanerozoic, Mesozoic and Cenozoic from bottom towards top. This first order pattern can be encapsulated as a trend of a rise during the Cambrian to a peak in the early Ordovician, followed by a steady decline through the end of the Paleozoic. Note this is 500 million years, so you can always find out in the graph where is the Precambrian Cambrian boundary, which was around 550 million year back. In the Mesozoic there is a peak of rise which can be plotted here, and this is coming within the Cretaceous top of the Mesozoic. And from Cretaceous onward there is this fall in the Cenozoic can be called as a steady fall. Now how we are linking these events with the plate tectonics? Sea level rose in the Cambrian as the new spreading centers formed between the continental masses, and then again fell as the continents regrouped during the late Paleozoic. When the continents were amalgamating, sea level was rising. Let us look at the second order cycles. which is presented in this curve. Even when we say that increasing sea level with time, if one observes the graph carefully, there can be shorter periods of fall and then some rise. So, in this portion we can see a fall. Such details can be called as the second order cycle. The reason of these second order cycle is that the rate of spreadings at the mid-oceanic ridges got changed with time, and that led to the second order cycles. The reason, change in rate of mid-oceanic ridge related spreading. Now let us look at the third order cycles. The second order cycles have their rise and fall durations of tens of millions of years, whereas in case of a third order cycle, the periodicity is of 1 to 10 million years, and the level of magnitude of rise and fall of sea level is only tens of meters. So, smaller time range and smaller difference in the water level characterize the third order cycles. The third order cycles are particularly relevant in sequence stratigraphy because they are the appropriate magnitude and period to be responsible for the cycles of sea level rise and fall that generates the depositional sequences. So, from the depositional sequences we can be able to pick up the third order cycles. The global sea level curve for the Cenozoic is presented here. Just have a look, and interesting fluctuation can be seen between the early Oligocene and late Oligocene. What exactly happened that led to such a drastic sea level change? In this entire span from around 60 million year till present, this much of change in sea level is most severe as per this graph. From around mid Pleistocene and in the Quaternary, the sea level fluctuations have become more rapid. In fact, it is most rapid when we compare from Paleocene to Quaternary. During the Quaternary, the sea level change detail has been studied through the oxygen isotope record, and here the cyclicity of tens to hundreds of thousands of years have been noted. Now, these global climatic variations have been related to the behavior of the earth and its orbit around the sun and changes in the axis of rotation. 3 orbital rhythms were recognized and their periodicity was calculated by the mathematician Milankovitch, and after whom these cycles have been known as the Milankovitch cycle. The longest period rhythm, approximately 10 to the power 5 years, is due to the change of the eccentricity of the earth's orbit around the sun. For an ellipse A divided by B, the aspect ratio, also it can be called the ellipticity. This R value for the earth's path, which is sub-elliptical, keeps changing. 2 paths are shown, path 1 and path 2. For path 1, the aspect ratio is R1, for path 2, the aspect ratio is R2. Clearly in the diagram, R1 is more than R2. As the elliptical path becomes more circular, the aspect ratio decreases. Just to note, in case of a circular path, the aspect ratio is equal to 1. So, the change in this aspect ratio leads to rhythm approximately of 10 to the power 5 years. The second change is the rotation. While the earth is rotating around the sun, the axis of rotation of the earth on its axis is oblique with respect to the plane of the earth's rotation, and the angle or tilt changes over a period of 40,000 years between 21.5 degree and 24.5 degrees. 100 kilo year cycle is related to the eccentricity. The 41 kilo year cycle is related with the change of the obliquity or tilt of the earth's axis. At present, the axis of rotation makes 23.5 degree. This angle is 23.5 degree. Now, this angle actually changes with time and is related to 41 kilo year of cycle or 40,000 years approximately. Now, the third important point, the shortest rhythm is 21,000 years, and it is caused by the precession or wobble in axis of rotation analogous to the behavior of a spinning top. While the earth is rotating around the sun, with this as the axis of rotation, sometimes the axis of rotation can completely change its direction. This tilt of the axis changes from being inclined towards the sun to being inclined away from the sun has a 22,000 years of cycle or 21,000 years of cycle. These are the three cyclicities encapsulated as the Milankovitch cycle. Now, these cycles working independently and in combinations are exerting fundamental controls on the global climate, leading to cycles of global warming and cooling, and hence the sea level fluctuation. The Milankovitch cycle can be broken into three parts: the eccentricity of the Earth's orbit, explained here, change on the obliquity of the axis of rotation of the Earth, and precession of the axis of rotation. These are the three parts of the Milankovitch cycle, and the cyclicities are different. For number 1 it is 100 kilo year, for number 2 it is 41 kilo year, and for number 3 it is 22 kilo year. The Milankovitch cycle significantly affects distribution of solar energy on the Earth, depends on whether the Earth comes closer to the sun or goes away, and especially at the high latitudes on the Earth, the Milankovitch cycle's effect is strong. Waxing and waning of Pleistocene glaciation has been linked with this cycle. We see the use of the word cycle in case of Milankovitch work and also in case of sedimentation. Is the meaning of cycle same in both the cases? Can the Milankovitch cycle be linked with the sedimentary cycle? Is it possible to study the sedimentary cycle and comment about the Milankovitch cycle? A few definitions. Fundamental cycle FC is the smallest resolvable vertical phase succession forms at a small scale cycle, and the succession can be less than 1 to 20 feet. So, we are here talking about the rock record. FC or the fundamental cycle can be grouped into intermediate scale cycle. These are highest order cycles and can be correlated over a large area. ISC can be nested into the third order depositional sequence, and the third order depositional sequence can be grouped in the second order depositional sequence. The third order depositional sequence can be defined in sequence stratigraphy. Therefore, we can summarize this piece of information in this way, that the second order depositional sequence can consist of several third order depositional sequence. These third order depositional sequences can be broken into several intermediate scale cycles. Now, these ISC can be broken into several fundamental cycles. So, this means the rock record can help to conceptualize the sequence stratigraphic framework. Now, some of these cycles which is found in sequence stratigraphy actually overlap with the Milankovitch cycle. The sedimentary record and its related cycle and the Milankovitch cycle can be matched. The Milankovitch cycle ranges from 10 kilo year to 2 million year. This is the range. In the valley scheme, the Milankovitch cycles are covered by the third to sixth order, and the important Milankovitch period of 100 to 20 kilo year consists of three orders. Whenever we are finding cycles in the rock record, it is produced due to an oscillating system. Oscillating system means an environmental situation E1 that led to deposition D1, then the environment shifted to E2 and D2 deposition happened, and then E1 came back, and then again D1 got deposited, then E2 came back, and then D2 got deposited. So, in this way we are getting an oscillation E1 to E2 to E1 to E2. This is the meaning of the term oscillating system. Let us look at the basic points in the Milankovitch cycle. Consider sun given by capital S, and here is the earth rotating around the sun. We are going to define the Keplerian orbital elements A, E, I, lambda, and then omega. So, there are altogether 6 Keplerian elements. A reference plane is fixed with respect to stars. This is the reference plane. Gamma and Z are the mutually perpendicular axes passing through S. Passing through Sun, there are two axes considered, gamma and Z. The plane along which the earth rotates is called the instantaneous orbital plane. Consider A and B are the semi-major and the semi-minor axes defined on the instantaneous orbital plane. So, this is A, whereas this is the center of the ellipse. B is the semi-minor axis. Now, eccentricity small e is defined in this way: a square minus b square square root divided by a, which can also be written as 1 minus b by a and then square root. Consider small I as the inclination of orbit with respect to the reference plane. So, this angle is given by I. Consider capital N is the ascending node. Here is the ascending node, and this ascending node is defined by the omega angle, which is the longitude of the node. This angle is the omega, which is the longitude of the node, and this angle is measured with the gamma axis. This is the gamma axis. So, we can write omega bold equal to omega, this symbol, plus omega. That means this angle is bold omega, this one, and this is known as the longitude of perihelion. This omega is called the longitude of perihelion. Now, we define lambda is equal to omega plus m, and it defines the position of the orbiting body. Say this is the position m, and suppose the angle also is capital M, then the lambda angle that defines the position of the orbiting body is given by this omega plus m. We can define the obliquity or tilt, which is epsilon, defined here, which is 23.5 degree or 23.4 degree in the present day. Scientists have found out the epsilon max, which is 24.5 degree, and the epsilon minimum, which is 21.5 degrees. The precessional index can be defined as E eccentricity multiplied by sine omega. Now, if we look at 1 million year back to the present day, so this is the Younging direction, eccentricity, obliquity and the precessional index have varied in these ways. And regarding the obliquity or tilt, epsilon, I have already referred that it is at present 23.5 or 23.4 degrees, whereas these are the maximum and the minimum values. Is the sea level fluctuation synchronous or coeval globally? We are not very sure. The local control can sometimes mask the global effect. For example, if a global curve is created for sea level rise and fall, and then within the known Oligocene strata there is a sea level rise, this portion we are talking, then if we find some other place in the world a significant rise in sea level, that can be correlated with the Oligocene profound sea level rise. Geochronology provides dates in this way for some event or some lithology A plus minus B million year or say billion year. Now, if there is some shorter cycles of sea level change, because of this plus minus B, we may not always be correlating the sea level change with some dated event or some dated rock body. In fact, the procedure of dating depositional sequences by comparison with a global sea level chart has largely fallen out of favor. That means, it is almost not practiced.